Morning. Morning. All right. Well, who here has been at my talk of yesterday? All right. Did you like it? All right. I got some good feedback. One of them was, Andrei, can you ever give a talk that is not revolutionary? The answer is yes, and the proof is this talk that's coming right now. So if you want something new, go for that. If you want something nice, come here. Otherwise, you can go right now. Another piece of feedback I got was very nice. Somebody told me, Andrei, you are the master of uncomfortable silences. Because you ask a question, and you have the guts to wait until somebody answers, until everybody in the audience feels hot in their seat. It's like, he's asking me probably. So he's looking at me right now. This is going to happen today, so be prepared. How about we build the slides? So make slides.ps and scp slides.ps to my site, and SSH into my site and call PS to PDF because I don't have it on Mac. For some reason, the Mac doesn't have PS to PDF, and then I'm going to SCP the PDF back to my computer here. And let's see if it works. Huh? 100%. Oh, now it's processing. So we got to wait for it to be copied back, and there we go. Whew. All right, that was a hurdle. So now we have them nicely built and fresh. And I'm going to talk about the topic for which I'm not the most qualified in the room, for the simple reason that you guys are awesome. And that awesomeness includes two particular folks. Anthony, who has been giving a great talk yesterday, and the tutorial the 2 days before that. And Mr. Hubert Thundering Voice Matthew, at least, not to mention Mark and other folks in the audience who I know for a fact are very good at this kind of stuff. That being said, I'm going to discuss code that is actually used in production at Facebook, on a regular basis. It is literally used every time you use the site. So that's pretty nice, right? I call the topic generic locking. To give you a bit of a background of how this came about, there's a story to this. So in the early 2000s, there was a huge battle of concurrent paradigms, so huge competition going on. And there are like a number of contenders, like patterns, let's say, message passing, lock-free, work stealing, automated parallelization. Detlef gave a great talk about this yesterday, comparing and defining properly and comparing all of these ways of doing things. And in a way, nobody won, right? Although, clearly before that, you had some sort of lock-based programming was the dominant paradigm and everything else was new. Right now, it's not a lock-based programming kind of disappeared and then it's not there anymore. It still remains a very important paradigm, and it's actually better than lock-free approaches in certain situations, such as when you want to set priorities for things. And they need to be different. Lock-free is like entirely all too democratic, if you wish. So lock-based programming, turns out it remains hugely important for C++ programs. Do we have agreement on this? Do you agree? Against? Again? Oh, no. So that was a bit of a latency there. Abstain? Like, I don't care. Yeah, I would take off right now. Go to that AngularJS talk. All right. So, now, actually, in 2001, I wrote a very controversial article, so I'm kind of building a waving together story here, right? So in 2001, I wrote probably my most controversial article in the C++ world. Volatile, this is actually a typo, but it's very interesting because it was auto-corrected. It was multi-threaded. I'm not kidding. The editor fixed that for me, and it's the first time I'm noticing it. Because, it's like I'm reading the slides, I'm kind of rehearsing, and I'm like, I know this title, so my eyes are going to skip over it. And at this moment, I was like, maltreated, which is actually kind of whimsical. It's interesting that that autocorrect happened. It's visionary, right? The maltreated programmer's best friend. Yep, multithreading is maltreating. All right, so that article uses a trick. It uses the Volatiles connection to the C++ type system, which is it's a qualifier like const or any other. I mean, that's it, like const or any other, or const or itself. It's a qualifier, and you can use it for overloading and for sort of defining methods that apply to threaded or non-threaded objects. And it introduced a nice idiom, which was, you know, whenever you have volatile, you can't use the object, and in order to get rid of volatile, you would need to lock the object. So it would use the volatile qualifier as an indicator that the object is locked or not. So it did not rely on volatile semantics. Anyhow, moving forward, in 2011, C++ introduced multi-threading rules for containers, and the way they work is the following. In C++, as of year 2008, this particular proposal was introduced. And let me kind of summarize it for you. If you have a container, an STL container, you can call const methods from different threads literally simultaneously. If you want to modify it, you can't do that. But as long as there are multiple calls into const methods, you can do it simultaneously. Okay? To continue the story, I'm going to go back a couple of slides. To continue the story, log-based programming has also made progress, even though as competition had intensified, right? Even though there are new paradigms coming, log-based kind of followed suit and just got better. To wit, only yesterday I was talking to Hubert, and he said, actually, there's new implementations of readers, multiple readers, one-writer locks, which are very good. They're just very good quality and, you know, kind of very refined and very subtle. So there's been a lot of improvements in CPUs, operating systems, APIs better, kernel level mutex is better user space, mutex is better spin locks, better readers, writer mutexes. So again, just to define terms a bit, could someone tell us what the many readers, one writer mutex is? What is that? Yes, please.
The writer can have an exclusive lock, but all the readers read at the same time.
So, right. So you can have many readers accessing entering the critical section at any time. But if a writer comes, it would have to wait for a readers to go away, right? And once it acquires the lock, nobody can either read or write. Okay? Question. If a writer is waiting and a reader is waiting, who should get priority? Somebody else. So if a reader, if I have so any number of, a million readers can be simultaneously, acquiring the lock, the mutex, right? So then if a writer wants to wait and there's other readers waiting, who should get priority? Yes?
The writer.
Why? The writer, why?
Otherwise, he will start.
Otherwise, it's very easy to start the writer for the simple reason that new readers can come at any time in the door at no cost to them, and essentially they would starve the writer away. Of course, there's more refined ways to do this prioritization, but in essence, you got to be careful with this kind of starvation. So, okay, great. So we can do one write access that precludes or other reads or writes, but we can do any number of read accesses. Excellent. So C++ 1x is serious about log-based programming. We already have a bunch of stuff in there, such as mutex, time mutex. Anthony knows all about it. Is the list even complete? Probably not. Recursive mutex, return recursive time mutex. And then we have shared mutex, shared time mutex. So these would be readers writers. And you have only in C++ starting with 17, you have the multiple readers, one writer lock, but it's available today in Boost, etc. Now here's the interesting part. Here's what I'm kind of getting. So there is a punchline to this. kind of building a story here. There's a punchline, which is the STD containers were designed for readers and writer. And let me explain why. So you have this, right? You have multiple readers, one writer. And then you have STL containers. And the STL container says, for const methods, you can have many readers. For non-const method, that means you're assuming you're writing to the object, and there could be no readers or other writers. Now, let me ask you this. Practically, to implement such a container, what rules would you need to observe? So to implement a container that can have in const methods any number of readers, any number of threads can enter the const methods of the container. Like if you implement such a container, what would you need to be careful with? Yes?
Not use mutable members?
No mutable members, thank you. Anything else? There's another thing. So no mutable members, because mutable allows you to cheat const, essentially, and change the object surreptitiously, right? And there's one more. Yes? Iterators will be problematic because they kind of look into the container, but they have their own life. But there's one more simple thing that you need to avoid. Yes?
No global functions?
No global data. No global mutable data. So you can't have global state kind of manipulated because again, globals sort of in a way allow you to cheat const, right? So if you observe these two simple rules, you can say, well, my container basically is obeying this particular rule. No IO, which is also for sort of a global thing. So you don't have to have like hidden mutation inside your const functions, right? So now let me ask you this. So we have two things. We have this rule which says if you have a container, as long as it's const, many people can call it. But if it's non-const, nobody else can use that container. And then you have the readers writer lock, which goes, you can have many readers for the subject, but one writer. Aren't these two, isn't there an eerie similarity between these two things? Right? So it's, at the wait a minute moment here, right? We have a wait a minute moment, which is, well, how about then I kind of make the two dovetail. So you have multiple simultaneous calls to const methods, no calls to const methods concurrent with calls to non-const methods, and you have user serial as calls to non-const methods, and this is the same exact thing for the writer. It's almost the same, almost the same bullets here, which is amazing, right? So this is kind of the nice thing that is noticeable. So you're looking at this, one-to-one correspondence. Am I making sense here? Am I gaining your trust here so I can trick you into using a template and something? And, I'm going to even pull a macro on you if I feel like it, right? So, okay, one-to-one correspondence, readers, writer, and const, non-const. Amazing. So whenever I call a const method, I need to enter read acquire. And whenever I enter a non-const method, I need to enter write acquire for the same lock, for the same mutex, same synchronization object. And it just works by that rule. So it works like today with the STL, just do it. So that's the idea. Now, we want to encapsulate all of this good stuff. And because of this rule and because of this this rule in the language, it becomes very easy to encapsulate and put together a little library, and you have it. So this is the idea. Let's keep a reader's writer lock outside the guarded object, and issue a read lock around each const method, issue a write lock around each non-const method. So now, okay, in order to do this kind of stuff, which of C++'s encapsulation mechanisms can you think of? I want to hook every const and every non-const method of any object. There is a type that does the same exact thing, which is a smart pointer, shared PTR. A smart pointer essentially hooks every method by defining operator arrow, and then it allows you to do things, right? So let's do that. How about the following? All right, let's get ready here, okay? Have a sip of coffee there. All right, let's see. So we have a template of any type and any mutex type, not any mutex, but a special kind of reader's writer mutex. So, you know, by default, it's going to be a shared mutex or whatnot. And we have defined a struct synchronized, which is going to hold the datum, right? And the datum is non-mutable. You don't cheat on the datum. And it has a mutable mutex because you're going to manipulate it even in const methods. And I'm going to define a little class LogPointer, which defines operator arrow. And I'm going to define for this very class Synchronize, I'm going to define its own operator arrow, which returns LogPointer. Similarly, for const synchronized object, I define a different operator arrow, which returns a const LogPointer, which has its own definition. Which is very similar to this guy. Now, explain to me, please, if I have a synchronized object like this, and I say object arrow method, what functions are going to be invoked and in what order? Yes, please.
The operator arrow is called recursively. First to get the LogPointer and then on the LogPointer object.
So the arrow operator is going to be called recursively. Notice the completely incorrect use of the recursive. I'm kidding. So it's going to be called transitively, for as long as it returns a non-pointer, right? Excellent, thank you very much. So I'm going to call first the operator arrow on this guy, on the synchronized object, and that's going to return a LogPointer. And the C++ compiler is going to be like, wait a minute, I didn't get a pointer yet for this operator arrow, so let me continue. It's going to invoke the operator arrow for this guy, the LogPointer. And then I'm going to get a T star, and finally the compiler is going to be happy. It's going to stop the recursion, right? It's going to stop transitively invoking the operator arrow, and it's going to call the method against that pointer. But there's one more thing that's happening, because this object is returned by value. It's an R value. So if I call an operator arrow against a synchronized object, several other things are going to happen. So why don't you continue telling us what's happening? So first thing that happens is, so I call this guy.
When we get the first one, and that will actually lock within the synchronized, that will lock the object.
It would call the constructor of LogPTR, whatever the hell that does, right? You don't know. I mean, I'm saving that, right?
Which requires, you need to require the mutex is required inside.
You don't know yet. So, you know, don't get ahead of me. What I'm saying is that this object is going to be first constructed, return from the operator arrow. The compiler is going to invoke operator arrow on this guy, and is going to finally get the pointer, after which the invocation occurs, whatever you invoked it for. And then, somebody else? What's going to happen after the call returns? The destructor of LogPointer is going to be invoked, and I'm done with the call. So by just writing object arrow method, I create an object, invoke a function, destroy an object in this order. Right? So you see, I'm very deliberately here setting you up for a lock method call on lock sequence. Better yet, in case I have a const synchronized object, I'm going to return a different type here. So I'm going to go through the same motions, except I'm going to create and destroy a different type of object, which, you know, you can see where I'm going with this. This is invoking the reader's lock, and this is invoking the writer lock. And all of a sudden, with essentially like this code only, I got one-to-one mapping between everything non-const and the writer lock, and everything const and the reader lock. All right. So let's see a bit of the implementation here. There's, of course, a lot of details to fill. So we have, I have a constructor here that's private. We don't need it. We have the default. We have Synchronize that takes a copy by const reference and by R value reference. these are sort of the usual suspects. One nice trick here is we have the conditional no except going on, which goes like this. Whenever you copy a synchronized object, it's going to be no except if and only if the value itself is no throw copy constructible. So that's a nice example of using a bit of introspection there to make sure that we propagate properly the capabilities of T, which is our generic argument, into the capabilities of synchronized. Makes sense? Did you know about this? Like no except, no except? So you have a few folks who don't. So it's very nice. Sort of no except is an attribute of the function. It's part of the signature, and it takes a Boolean. It takes a Boolean as an argument. You can write no except and put no paren and no Boolean, and that means it's never going to throw. That's not entirely true, but anyhow. So it's the user makes a vow, a pledge to not throw. That's probably more like it, right? Like, in C++, never is, it means almost never, and always means almost always, except for this long list of exceptions. And this is no exception. Gee, wow, 3 meanings of the word in one sentence.
Unless it's statistically almost never.
You have to disagree on, yeah, never say almost never, except, okay, so no except, just say no except, it means I'm making a vow here to never throw. But if you put no except and you open a paren and you put a Boolean constant in there, it's going to be no except or not depending on the Boolean, if it's true, And in this case, it turns out there's this is no throw move constructible standard introspection facility, which cannot be implemented in standard C++. It's magic. So you can't sit down and implement it. The compiler has to define it for you. And the compiler side is going to use some underscore things to implement it, but it's not implementable in user code. It's an introspection primitive. And the same goes about no throw copy constructible, which is also magic provided by the compiler. So by this I'm saying, well, if the original type was copy constructible without exception, then I'm going to not throw from the synchronized constructor as well, which is as expected. When you build from a piece of data, you actually don't need to lock anything, because it's just, just building the object anew, so there's no need for locking. There's no multiple threads accessing this constructor. So again, there's this whole no except trick again. So with assignment, we have an interesting thing here to worry about. Who's been in Anthony's talk yesterday? Okay. Anthony made a very good point yesterday, which was if you have any piece of code that needs to acquire more than one lock, they need to be acquired in the same order in all threads. Because if not, what's going to happen? Somebody who hasn't been in Anthony talk, let's think real time here. So if one function acquires lock 1, lock 2, and the other function acquires lock 2, lock 1, what's going to happen? Yes? Deadlock. How is it occurring? Someone in the front, because it's easier for me to hear. How is it happening? How's the deadlock occurring? Yes?
One thread is waiting on one lock and the other one is waiting on the other lock.
Right, so it just happens, it doesn't always happen. It only happens when one thread got so far as acquiring one of the two locks, and the other also has gotten to acquire the other of the two locks, and then they both wait for each other, and they never release. So what is the obvious solution to that? Yes?
Cycle detection.
Cycle detection. There's an easier solution, actually, to that, which is here. Lock in increasing order of the address, because the address is unique and ordered for the whole application. You don't care what the order is. It just has to be the same. So that's the clever thing here, right? So to be like more Catholic than the Pope himself, I just say STD less of void star, which is a guarantee that I can compare pointers for inequality regardless where they come from. this is the standard way of saying I want to compare two pointers. They're not in the same array. They're not in the same object. Did you know this? This should be common. Everybody should know this. And everybody knows it starting like as of a second ago. Awesome. Great. So, it just use this less thing, and on these flat memory systems of today, it just works automatically. But remember when you were kids, there's a thing called segmented memory architecture. Did anybody work with this? Okay, some of us do have the gray hair to prove it. Or no hair at all. Well, the bald thing is in vogue right now, so I should try it. So essentially, like in those days, you would need to do some pointer adjustment, so the comparison would be more complicated and more costly. So therefore, you would need to use this less thing. All right, so all I'm saying is that if this is at a lower address than RHS, you lock in the order of this and the other guy. Otherwise, you lock in the other order. And that way, the assignment of two synchronized objects proceeds nicely. Right? And we have a number of other usual suspects, such as move assignment, swap, and such. Right? Awesome. Questions so far? Okay, let's recap the basic plot here. Let me see what. Okay, excellent. So before getting into the implementation of the operator arrow, let me share again the basic plot I'm following here, just to make sure we are on the same page. So we built this synchronized type around the following realization, which is the new C++11 rule guarantees that I can enter from any number of threads the const methods of a container. Right? At the same time, if the method is non-const, I could allow no other const or non-const method to be executed concurrently. So I need to do locking. Taking the, yes?
Regarding the assignment operator, just continue.
No, go ahead.
The assignment operator, just a question about the
Yes.
invocation of the arrow operator there. It does this LogPointer temporary, right?
Yes.
But the destructor is called at the end of the block, right?
No, because you create objects here. So you create actually named objects which are going to be through the end of the scope.
Okay, so the LogPointer.
Yeah, so these G1 and G2 are these logPTR types, and they're going to exist until the end of the scope. Okay, actually, I did have a moment when I thought, oh my God, this may be all wrong. But then I thought, this type is used a lot inside Facebook. So if there's a big mistake like this, I'm sure it would have been discovered by now, or not. And so that when Facebook fails, people call 911, and there's this this issue. Moving on with sort of the recap. So my plan here is to say, well, we have const methods, many readers. So the const methods would be the many readers. And the non-const mutating methods would be the writers. And then I have this nice correspondence, so I can use const as my trigger, my indicator for whether I want to lock the object for reading or writing. So that's my plot. That's my basic. This is sort of the discovery we've made that allows us to implement this abstraction. Without that particular rule in C++, you can't. And actually, let me tell you this. This was the case before C++11. All C++ implementations I know of had containers that obeyed this rule. So this was just simply enacting into law what was de facto true, which was STL containers never use mutable data and never use globals, because people noticed a number of issues with those related to threads or not. So there's actually in the 94, there's kind of a transient issue with that, and people are going like, you know what, no globals, no mutable data in STL. So this was kind of the case before this, and I'm very happy it became law, because then it allows us to do this. So, all right. So we have this, this operator arrow, which is going to be overloaded for constant and unconst objects. And this little thing here allows me to choose whether I use read locking or write locking by means of the return type. And then the return type has its own arrow. Great. All right. So moving on with the implementation of operator arrow, the locking pointer, which is kind of inside the synchronized, holds a pointer to its parent, and it does not have a default constructor. It doesn't make sense to create a default locking pointer object. Its only raison d'etre is to just be created as a temporary from operator arrow from the synchronized guy. So, you know, simply locking pointer, synchronize star parent, stores the parent, and mutex lock. Boom. So that's my locking pointer. What do you think the const locking pointer constructor looks like? Yes?
Same, but mutex share.
So it's going to be a shared lock here, a different call. This is acquiring the lock in write mode, and this other guy is going to acquire the lock in come on. Okay. Oh man, I didn't write that. Okay, well, I'm missing a slide here, which was very nicely. So the next slide should have been the identical code, except the name locking pointer would be const locking pointer, and this would be a call to shared lock. Shared lock, right? Okay, so as a small details, you should know that readers, writer mutexes are recursive, so you can lock the same thing multiple times, which is nice, and you kind of, you know, it's convenient. When you assign a lock pointer to another, you just have to make sure there's no self-assignment, etc. So this is just for optimization. You could actually acquire it twice. All right. Whoop. So for efficiency, you also want to implement the move constructor, which takes a R-value reference to the other lock pointer. And again, you make sure you don't self-move assign, which would be very, very bad, but it's still legal. Is that right? Can you self-move assign? Are you allowed to? I'm seeing some raised eyebrows up to the ceiling there. I'm seeing a sad nod from Detlef in the back, and just like telling you people what's happening in the room right now. So yeah, it's very bad, but it does happen. People kind of do it. They shouldn't. But just for, this is like code for bad people, it's going to support them. It's going to make them happy. All right, so awesome. And what else? Oh, yeah, you can't move construct an object into itself. That you're not allowed to. Although you syntactically can. You can move from a non-existing object into itself. Well, this is C++ for you, right? There's always, you can construct these sentences that kind of parse and then like, well, that can't be, right? So, okay, so in the destructor, obviously you're going to unlock the mutex if the parent was not null. And that sort of, you know, completes the locked pointer. So, you know, it's all boilerplate and it's all simple code. The nice thing is that it's highly reusable. So, okay. The whole point of the lock pointer was to implement this operator arrow, which simply just returns the data. No problem. Of course, if you create a lock pointer and you move from it or something and it gets to the null pointer, if you try to invoke the operator arrow, you're going to get a segmentation fault, which is, you know, pretty much what you deserve. Right? Excellent. We pop out of lock pointer, and at synchronized level, as I promised, we have an operator arrow non-const, which returns an R-value of type lock pointer. And this completes the lock pointer part. So whenever I use some SPTR arrow XYZ, you have two invocations of operator arrow. One for the synchronized object, the next for the lock pointer, and then you get the object, and then the lock pointer gets destroyed, and the whole locking and unlocking mechanism is automatic. Const lock pointer looks a lot like, and it's essentially the same code, as I said. It's pretty much just the same, except you're going to call parent mutex lock unlock shared. Right? So you're going to call different methods. Right? All right. Who can tell us what cBegin and cEnd do in C++ 11? cBegin, cEnd, yes. They return a constant iterator for a mutable object. Right? For a like non-const, regular container, they return const iterators. Do you need them? Are they necessary? Are they necessary, or are they convenience? Well, they're convenience, and I'll tell you why. You could take the container, cast it into a reference to a const container, and then take begin from that. And that's my cBegin. But it would be through 2 lines. And a new variable. It would be ridiculous. So I insert a const cast like an idiot there, and I put like, const container, and then I make a typo, and I cast to something that I shouldn't be casting to, and you don't want all that. So cBegin is a convenience function that says, even though I could mutate this container if I so wanted, I'll be good today. I'm not going to mutate it. So let me call cBegin and cEnd. Is that right? So for the same reason, sometimes I want to be nice to an object I could mutate, and I say, actually, I want as const. I want to look at this object as if it were a const object. So then you can say sptr.asConst arrow method, and that's going to acquire which kind of lock? Which lock, the reader's lock or the writer lock? The reader's lock, right? The multiple readers, because it's a const object, is going to invoke the method. So that's a nice convenience function. So now it gets to the fun part. So whenever I talk about anything really, at some point, if I have a macro, invariably there's going to be like 3 dudes at the end of the talk saying, that macro, let me ask you a few questions about it. I'm not kidding. Like it fascinates people. It's like, I don't know, it's like people are weird. Like that. That is the, I don't know, adults only section of my talk. It's like, you know what, I have to ask you in private a few questions about that macro. Because I found it very interesting and dignified with, I think it's good to talk about it. And I'm going to use this for the rest of my life, right? So this is going to be fun. So, here's the thing. I'm going to do something stupid. Here's something stupid I'm going to do. Who can spot the huge mistake I'm making here? Yes, please. Yeah, this is kind of a rookie mistake. So SV is like a synchronized vector, right? Very nice. Well, let me test if it's empty. SV, acquire a reader lock, call empty, get back from the reader lock, unlock. And let's say it returns, it's not empty. Boom. Okay. So then I open a scope here, and I'm going to say, oh, if it's not empty, I can access the front right now because I'm so smart. So good, right? And this is going to acquire another lock. And of course, in the meantime, between the closing of this particular parenthesis and the opening of this guy, like this, there's an eon here. There's an infinite amount of time in theory. You could think an unbounded amount of time could occur in there. And, the other threads may have a party right then. They're like, this is awesome. I'm going to lock and unlock the object and manipulate it any way we want, including making it empty. How about that? So then I'm going to take front of an empty vector. So you can't use the object that way. And actually, I've been criticized by people at Facebook who said, you made it too easy to do this. Because people just write an arrow, and then whenever they write an arrow, there's a lock and unlock happening. And I'm like, well, read the fine manual. RTFM, right? Redefine manual. So, all right, what's the cure for this? What is the cure for this? Yes, please. Right, so I need some sort of, I need a mechanism to be able to lock the whole SV thing and then use it in, inside the critical section and then be done with it. So, I've been thinking about this for a while, and I found something that's very nice, except it uses a macro. Here's what the trick is. I define a pseudo statement, which is called, obviously, synchronized in all caps, because we like to shout when we write macros. Synchronized SV. And this is the use. So it's almost like magic, because inside synchronized, it's a critical section, and I can use SV as a vector. So I can write SV dot empty instead of SV arrow empty. So inside the pseudo statement, I have an already locked vector. And if it was mutable, it's going to be acquired for write. And if it was not, if it was const, it's going to be synchronized for reads only. So now I can call, inside the synchronized section, I can call any method on the vector because SV was mutable. So inside, SV is an L value of type vector int. And lock is, in effect, I can use this vector. Notice something interesting. This macro not only does the locking and all that stuff, but also it changes the type of the name SV from synchronized vector to vector. Do you want to see the definition? Are you up for it? All right, do you have that blood running through your veins right now? All right, this is it. I'm not kidding, this is it. Oh man, it looks ugly. It's only now I'm kind of, oh man, this looks really bad here. All right, so, all right, this next section is like Andrei tricks for writing macros. And trick number one is you want to inject things into a new scope. Then you have these if statements and these for statements that all they do is kind of inject names into the upcoming scope. So first, I define an if bool underscore 1 equals 0 like an idiot, and I do nothing. And I say else. And that made available for me a Boolean variable because I want to play with it. And then I have a for that does pretty much nothing because it's going to last until like not underscore 1. It's going to run exactly once. So I have a for, and it says auto underscore 2 equals x, which is my argument. Operator arrow, So at this point, I'm acquiring the lock. And then I'm going to do this, stupid thing that essentially makes the loop run exactly once. And then I'm going to take, so here I'm taking the locking pointer, and at this point, I'm taking the vector, which is an L value, and I'm calling star underscore 2, which is my locking pointer operator arrow. So I need to call by hand, I make by hand those two calls to operator arrow that we're talking about. They're done automatically by the compiler otherwise. In the macro, I'll do them by hand. So at this point, notice that I introduce x, which is a template, a macro parameter, and effectively x is going to shadow the name x in the scope that's above it. And I redefine x to be, this time, a reference to, in our case, a vector. Yes?
Does the compiler not do the arrow trick for you then in this case? Why do you do it by yourself?
Does the compiler not do that trick for you? No, because what I want to get is not the pointer, I want to get the reference. So if I want to get the reference, I need to do them by hand. Right? All right. So, all this guy does, one is limit loops to one pass. As you see, there's the not one, and one gets like, there should be true here just to be nice, but I didn't have room on the slide. There should be true. I'm not kidding. Actually, there's no room on the slide, so I could use one. Right? It compiles and runs. So it gets, actually, I've checked. It does get optimized away. All that Boolean nonsense, the compiler's like, this guy must be an idiot. So, okay. Let me compile this better for him because I'm not sure what's wrong with that code, but I don't care. So, okay, fine. First loop creates a locking pointer. The second is going to take from the locking pointer the L value and is going to shadow the object with an object by the same name. And this macro actually does everything, all of that allows me to do this. Cleanly. Very nice. All right. There's an issue though. What if I have, and careful here, is not a synchronized vector, it's a vector of synchronized. So the synchronized is inside each vector element is synchronized, has a lock. Right? So not the whole vector is synchronized, but only what's inside. And now I want to say, well, I want to synchronize on this vector front. What's going to happen there when you expand the macro? Who can tell us? Yes?
The variable names will be long.
So remember I said this x here is a macro parameter, it's going to shadow whatever, but in this case I call synchronize with an expression, it's not a name, it's an expression. So the compiler is going to be like, you are an idiot because you're trying not to define a name, but you're trying to define an expression as equals something, which is ridiculous, right? You can't do that. So this is not going to work. As soon as you have an expression here that's not just exactly one name, you can't use this. So, I lost a few nights of sleep over that because I was, so I need to kind of create like a temporary here and it's not pleasant. Here's what I came up with. Well, when one argument is not enough, I'm going to define two. So synchronize with two arguments, and this is my name first, and I'm assigning it from vsw.front. And inside I'm going to use the name first. Now, anybody who's ever written one macro is going to know that we're entering dangerous territory here because we have the same macro name used with one argument or two arguments. And you kind of has got to distinguish the situations. Do you think it's doable? No, honest, because I thought it's not doable for a long time. And then, I don't know, one day I had the divine inspiration, so I did it. So here's how it works. I'll start innocently. Define arg1 of A and any other number of parameters, A. That gives me the first argument of any number of arguments. Nothing on my sleeves. Define arg2 or 1. So if I call arg2 or 1 with two arguments, it's going to give me the second argument. But if I call it with one argument, it's going to give me the first argument. And here's how it works. Arg2 or 1 IMPL, VA args, comma, VA args. And R2 or 1 IMPL of A, B, and any other argument is going to return B. So now let's see. If you call R2 or 1 with one argument, X, it's going to expand into R2 or 1 IMPL X, comma, X. And then is arg1 2 or 1 IMPL of X, comma, X is going to expand to it's going to expand to X, comma, X. It's going to return X, so that's what I wanted, and I'm done. How about we call this guy arg2 or 1 with X, comma, Y, two arguments, right? In that case, I'm going to expand it to X, comma, Y, comma, X, comma, Y. X, Y, X, Y, right? Because I'm doubling the variadic arguments here. And in this case, it's going to go into arg2 or 1 IMPL of X, comma, Y, comma, X, comma, Y. So it's going to give me Y. So if I call it with one argument, it's going to give me that argument. If I call it with two arguments, it's going to give me the second argument. So I have two macros. Give me the first argument, give me the second or first argument. Are ready? Ready for the next level here? All right. So we're there because we get R2 or 1 of VA args, and I'm getting arg1 here, and it turns out it just works that way. So if you invoke this guy with synchronize with one argument, you're going to get just like before. But if you invoke it with two arguments, this operator arrow is going to be the second argument, call against the second argument. And in this case, I'm always picking the first argument to define the variable. So this very macro is going to be usable with this idiom and that idiom, which is awesome. I'm very happy. I gotta tell you, this is one of those dirty pleasures of life, right? It's, I felt very satisfied in a shameful way, I should add, by having written this. Okay, great. So now, so recall C begin and C end. We sometimes want to specify, even though this particular expression is mutable, I just want a const lock, a reader lock. So in that case, it's good to define a new macro, which fortunately can reuse the existing macros. So we're good. We just use this asConst method here. And whenever I say synchronize const, you know that inside you're going to have a reader lock, and you'll be able only to call the const methods of that guy. So terrific. All right. So this code, yes?
Is this macro used in Facebook?
This macro is used at Facebook. And actually, there's 7,000 something uses of it. Is that right? It's in the thousands of users. Of course, the code base is much larger, but it's used intensively. Yes. You don't get shadowing warnings all the time? No, actually, I'm not sure if that warning is explicitly suppressed or if it's just, do you know? Okay. Well, I got to get back to you on that. So I remember there's a discussion about that, and people are like, you know what? I like shadowing things all the time, so I'm not going to. Oh, and actually, I remember the problem. There are some globals that people defined, and these shadowing warnings were too many false positives, and people didn't like it, so they didn't enable that warning. I remember Jim Myring, a former coworker, he really wanted to introduce this warning, and everybody protested, so it didn't, it didn't take. Yes. Can you implement this as a function taken lambda? I think you can implement this as a function taken lambda instead of a macro, right? Yes. It would be a bit more quirky syntactically, but you can do it. You can say, log this object, call this lambda, unlock the object. Yes, Anthony.
Yeah, there's I've got a standards proposal to rewrite that has an apply function that takes a lambda.
So there is a... So it's not there yet. It's going to be in year 3000 or something. Okay, awesome. Thank you. That's great. Yes.
Did you have, because you wrote the original article about using volatile, did you have any argument to use volatile instead of using constant for the same thing?
Did I have any argument of using volatile? No, actually this works better because I noticed that people have a very strong emotional reaction when they see volatile. They oh, this can't possibly work. And they stop there. It's like a psychological barrier that I found it's unpassable. So I'm very happy that this whole constant mutable thing works properly with STL containers. And it actually works with a lot of user-defined data, to be honest. You don't use mutable data every day, and you don't use static state every day, right? So I'm happy with the state of affairs, and I kind of reneged that old article. Yes? As long as you don't have operator dot.
Isn't the usage of the macro confusing as you use arrow syntax outside the macro and dot syntax within?
Is the macro confusing by the use of the arrow if you want to lock the object on the fly versus dot if you don't lock the object on the fly? This comment came a couple of times, so let me kind of make sure I understood what you mean. So I mean this, like arrow here, right? And here. Yeah, so so here you use the dot, and if you don't use a synchronized pseudo statement, you just use the arrow. People mention that actually, let me add this. It's easy to implement the macro to force you to use the arrow in both cases. I chose to allow people to use the dot because that pointer can never be null. So I'm not, I don't think it's a huge problem. I think people just get used to it.
But
Yes?
instead of a magic macro, would it be possible to have just like an acquire call in the synchronized object, which return a reference to the mutex, and then you could use a proper lock or shared lock, and it would be more obvious to the reader what is happening?
Can you use an acquire method in the object that returns a lock?
No, a reference to the mutex inside the synchronized object.
Well, I got to take this offline because I'm not sure I understand how this would work. So it would be instead of the arrow, there would be an explicit call?
So instead of the synchronized macro, you would call sv.acquire. That would return a reference to the mutex inside, which you could then use within a shared lock or lock, like a lock bar or something.
I guess you could, so just to make sure I understand, so essentially instead of the synchronized macro, you would have a method and it would return an object and then you use that object and then get rid of that object. And is that?
You would get a reference to each object.
You get a reference to yeah. Yeah, I got to look at it to make sure how. But anyhow, you open with, instead of a magic macro. At that point, my brain stopped because no, instead of a magic macro, it was nothing else. I would use a magic macro, period, thank you very much. So a magic macro is kind of cool. And I have the suspicion that the C++ standardization committee defined apply just because they didn't know how to do this args1 and 2, this thing. How about that? All right, so further reading. We're getting there. All right, further reading. So just Google for folly synchronize. You're going to find it on GitHub, in Facebook repository. It's I'm very happy to report that it's been used. It's been used quite a bit. There's there's a number of other methods that I didn't discuss because they're trivial. There's time locking. There's an interesting other magic macro, unsynchronized, which inside a synchronized statement, it just so happens sometimes you want to get rid of it. So you have synchronized, you open a scope, you do ta-da-da-da-da, and you're like, at this point I'm kind of tired of being synchronized, so let me unsynchronize the following operations. So you open a new scope with unsynchronized, and then you write some unsynchronized code, then you close that guy, you're back to synchronization. It turns out it's good to have. And synchronized dual is a macro that allows you to synchronize on two objects at the same time by doing that trick of locking them in increasing order of the address, right? So I can take a few more questions. Yes?
When it becomes so easy to wrap interface concurrently like this, can it easily happen that you do make concurrency errors using the API, like this non-if, non-until upfront?
Do you allow concurrency errors by using this things like this?
Does that happen often, and it's so simple to wrap a class in a synchronized version?
So you're asking if I'm making it too easy to?
Yeah.
Okay. That argument can be made and has been made. So on the other hand, this is C++. I mean, you're trusting whether people know what they're doing to some extent. And it turns out very often for highly granular objects, you do want to lock the object, call a method, unlock the object quite often. So, I'll let you two to decide. The argument can be made. I do agree. I could be more difficult, like just say sv dot, make sure you know what you're doing, open, close paren, that kind of function. Yes, there's another. Other questions? Yes.
How's debugging?
How's debugging?
Stepping through all these magic macros and stuff. Is that
I'm having difficulty answering this question because, how's debugging going with, step-by-step debugging and stuff? I'm having difficulty with this question because I never need to debug my programs. It's it's an unknown territory to me. All my programs work from the first go, so I have no idea. I suspect debugging goes just, macros have the usual issues debugging. Step-by-step is going to keep the object locked inside the synchronized method, so it's probably the usual suspects. But I don't think there's anything sort of new or interesting in the debugging space brought about by the use of these functions and macros. Yes?
Seem to remember the original LogPointer that casted away volatile.
Yes.
There you could kind of make the transaction, because then you could return, take the LogPointer, you could return a reference to the object inside and use it for multiple operations until you release the log.
So getting back to the LogPointer that used volatile and non-volatile, and you'd, yes. So what's the question?
No, the question is if you could use kind of the same idiom here that you kind of take the cast so that you get the reference, but you're still holding
Yeah, you could. So if you could take sort of a temporary object and use it in knowledge that that's a locked object. Yes, definitely. I think there are a number of other idioms that you could use around this C++ standard rule about STL containers. So I happen to like this one. It's very convenient and very terse, but definitely you can make it more explicit if you so wanted. All right. Last question. All right, you've been awesome. Thank you so much. Thank you.
It's fun to see you back.
Thank you. Thank you very much. Thank you.